Hello everyone and welcome. Today we are going to create our own chess game in Python. Before we start, I just want to note that this video is not suited for people which has no coding skills at all, or which have no programming knowledge, zero programming knowledge. But it's perfectly suited for junior programmers or beginners. So let's just go ahead. For the purposes of our chess game, we are going to use two libraries. The first one is Checkmate. I'm sorry if I'm pronouncing it wrong. It's maybe not as popular as some Pygame or some others, but it will definitely serve us well. It has everything what we need. Another important library which we have to import and which we have to download it at first is the PIL library or PIL library. This library is used for working with images because we are definitely import images into our game and we are going to move it and work with it. So if you want to import if you want to use this library, you first have to install it through pip. So we are just typing install below. It can happen that you can get some error message, or you can receive some error message, something like pip is not recognized as internal or external parameter. If this happened to you, and below in the description I have described how to overcome this problem, and I hope it won't be nothing difficult for you. This should not happen if you have installed the Python properly, or if you are not on your business notebook or something like that. But this PIL library we are not going to use or not going to import in this file. Maybe let's talk about some plan, what we are going to do. We are going to create a couple of classes. The first class will be representing or will be responsible for visual representation of the whole game. Let's call it board graphic. Then another class, I will split it into another file. We can call it board state with uppercase. Board state. This class is going to store all the necessary information about the current state of the board, and then we are going to create the very last one class. It will be called piece. So definitely we need the class piece. Then later on we will create another classes which will be inheriting this class piece. We will create class like pawn, king, queen, rook, and so on. So for every single type of piece, we will have our own class. And of course, all of them will have something similar, something what is totally same for every single one. So all of them will be inheriting the class piece, but of course all of them will have the different rules and so on. Let's create at least some first look how our chessboard could look like. So definitely we need to initialize our class. I am going to define some values here. The first value I'm going to define is the square size, and this is the very last hard-coded value. My strategy is that I just want to define only single one hard-coded value, and all other values, which will be representing some sizes of some another graphical objects or things on the board, will depend on this only one value. For these purposes, we will need to use a little bit of math, nothing like difficult, but it could be maybe a little bit overwhelming. You will see later on. If you do not feel comfortable with this, you can hard code all the values. During programming, it will be definitely easier, but later on, if you would like to adjust the size of your game when you will want to run it on different desktop or different display, then it would be definitely much more difficult and messy. So I'm going to use this strategy to define only single one hard-coded value. This will be the size of single one square. Of course, we are talking about 50 pixels. That's our measure. We are measuring in pixels. And of course, we are defining a self in order to make this variable visible for the whole class board graphic, for all other methods, not only for this initial method. Then we are going to define a label size. Label, I hope it's called label. I mean by this the border around the board where are numbers and letters, like from A to H and from 1 to 8. So our label size will be like square sized divided by 10. It will be like 5, and we can multiply it by 2, let's say. Then we have to define offset. Our offset is like the space between the border of the canvas. The canvas will be, of course, our background. The canvas will be the place where everything is going to happen. So offset is the space between the canvas and between the board or border of our board. So our offset will be, let's say, label size multiplied by 2. Okay, then we need a board size. That will be nothing else than just square size multiplied by 8. Let's define the sizes for our canvas. So we definitely need to define the canvas width. It will be, let's say, board size, of course, board size plus offset multiplied by 2, because if you can imagine it, it will create like a space around it. And also we need to define the self canvas height. For now, it will be the same, of course, because chess game is square. It's 8 times 8 squares. But we are going to change this value a little bit later on, so I'll just keep it like this. And now we can set up our canvas. So like at first we need to define the root. Root is actually, or this our self root is taking inter.tk. It's going to store a reference on the top level window of our taking instance. And of course, with this top level window, we can interact later on. Then we need self canvas, and this we can initialize this way. We need our self root. We need our self root, and we need the sizes. So we need the canvas width and canvas height. So attribute width and attribute height. Okay. Now, of course, this is like the taking inter thing which you have to do. You have to pack it. If you want to this, it would be like, it's not possible to create the canvas without this pack method. Now let's define some colors which we will be using. I have here some pre-prepared colors because it was one of the most difficult parts to choose the right colors, and I will just type it here. We are of course using the hexadecimal format. So on the websites, many websites, you can find the RGB palette. You can choose the color you like and then just convert it to the hexadecimal value. Okay, so now let's create our method called initDraw. InitDraw method will be responsible for a visual representation. We are going to use the very first method of our canvas object. It will be create a rectangle. Here we are defining let's say 4 values, but I have divided into 2 tuples. First tuple will be representing the x and y coordinate of the upper left corner, and second tuple will be representing the x and y coordinate of the bottom right corner of the rectangle. So we are now going to create 2 rectangles. First will be representing the border of the whole board, and second rectangle will define where will be the label for our symbols, for letters and numbers. So x and y axis for upper left corner will be self label size for x and self label size for y. And then let's define a bottom. So we're going to use this variable further. Self board size plus self label size multiplied by 3. As you can see, I have been mentioning at the beginning, this math could be a little bit overwhelming for someone. So if you are feeling more comfortable with defining fixed or hard-coded values, then just go ahead. And then we have another rectangle, which will be representing where the label will be. So for this, we will use an offset for x and offset for y, and bottom minus self label size, and here we're putting very same value. Now if we want to call this method by the initializing, we of course need to define it here in init method of our class, so init draw, And if you want to see what we have created, let's create a variable where we will be storing a reference on the board graphic object. And if we want to see it, we need to use this main loop method. Without using this, our board graphic will display just once, and then it will be closed. The instance will disappear for us. But with this main loop, we are now saying, no, do not close it, just keep running it, and I will define when I want to close it. So let's just look what we created. Okay, this is pretty nice. Now let's just put squares inside. Of course, what do we need? We need the squares inside. For this, we are going to use a for loop. So for row in range 8, of course, because we have matrix or like 8 times 8 board. And now for column in range 8 again, we want to create a lot of rectangles, and for this we can define an x-axis and y-axis. X-axis will be self-offset plus column like a column, of course, multiplied by square size, of course, because we want to increase the value. We want to increase how the x-axis is going to move to the right. So there is almost the same thing for y-axis, but here we are changing it according to the row. Here again we are defining two tuples, x and epsilon, and this will be, this is for upper left corner, and this will be for bottom right corner. It will be almost the same, with the difference that I want to increase the value by square size, and here I'm going to do the very same thing. And let's take a look. Okay, this looks pretty nice. We have beautiful grid here for our chessboard, and now we want to fill it with colors. I have prepared my colors here, so feel free to pause video and to choose your own colors, or just to copy paste those as you want. For this purpose, we need to add another attribute for our create rectangle method. It's called fill, and we will be filling it with the variable color. We want to change the colors. How can we achieve this? At first, we need to define the variable color. I want to start with the white color, so that's why at first my color will be black, and I'm choosing such a strategy that during every single loop, I see, I will check, okay, is my color black? Then I'm changing it to white. Is my color white? Okay, I'm changing it to black. So I will do it on using a one-line if statement. So my color will be self white if color is equal to self black. So as we can see, after very first run of the loop, we are changing the colors. And else color will be equal, else color will be equal to self white. So now we are changing colors row by row. We also want to change it column by column. So let's just take a look if it works. Self white, self black, self black. Yes. Sorry, I made a mistake. So now now it works properly. So now we have a beautiful chessboard. Now we want to put symbols right here in my space for a label. So here will be letters from A to H, and here also here. And on sides will be numbers from 1 to 8. I will just use two lists which I have prepared before. So these are my lists for symbols, and I'm again going to loop through the range of 8 in order to put all my symbols where I want to have them. So I can call for symbol for S in range 8. I will define a step. This will be like the variable which will be changing. We just want to move forward, so when we are putting the letters up or button, we want to change our x-axis. So our x-axis will be moving forward to the right. And by numbers, when we will be talking about numbers, we want to keep our x-axis, but we want to change our y-axis. But both coordinates or axes will be changing in the same way. So our step will be self offset plus self square size divided by 2. Yes, divided by 2, because we want to put our symbols nearby the squares but in the middle of them, plus self square size multiplied by S by symbol. This will be our step, and now we are going to use a second method of our canvas object. It will be create text. Now we don't need like 2 pairs of x and y coordinates, we need just one, and this x and y coordinates will be defining middle of the text, very middle of the text. So now we are talking about letters. So x-axis will be changing, and y-axis will be self offset minus self label size divided by 2. And we can put this into tuples to make it like more readable. And another attribute which we want to define is text, and our text will be the element from the letters. Very similar thing we want to do here on the bottom, but we want to change our y-axis. So we can say self board size plus self offset plus label size. Yes, plus label size. And very similar thing we want to do for numbers, but with one difference, that we will exchange the step with this. So this will be our x-axis now, which is fixed, which is not changing, and our y-axis is now changing, and also here on the right side. So step. Okay, let's see what we have created here. It looks pretty good. So as we can see, the very first thing, we are adding the letters from our list letters on the top, and we are moving by one step, and the y coordinate is staying the same. So we have finally our very first visual representation of our game, and now we want to move forwards to the more interesting part. So let's just define the board state class. So of course we are going to initialize it, and during initialization we need to interact with our board graphic class. So that's why we need as initialization parameter our board graphic, and also we need a canvas from our board graphic. This will probably make more sense later on, but from board graphic we need some values or like sizes and also colors and so on, and we need a canvas if we want to like interact, if we want to move with our pieces and do all the stuff which are needed when you want to play chess. So let's just define it here. So let's say board state, and I want to initialize, sorry, at first I need to of course import this. So from board state import everything, doesn't matter for me right now, self board state board state, and I need myself, like when I'm in board graphic, I need myself when I want to initialize this object, and I need self canvas. Now we can work with all those things which are included in the board graphics. Now let's go further. So we need self board graphic, and my self board graphic will be of course nothing else than this, and our self canvas will be equal to canvas. And now we want to create, actually the most important thing from our board state, we need to create a board. So we want to initialize a matrix, a list of lists where will be stored references on the objects, on the types which we will create later on. So we need self, and here we need to return a pretty big list. So how do you want to make this? If you can imagine that we will be moving with our pieces through our list. So for example, let's say I want to move with my pawn one step forward. Then I will literally move him from the place in the list where he was at the beginning, and we move him one row above in the same column. I hope it will make more sense when I will be doing the whole thing. So we need to at first create those types of objects like rook, pawn, etc. But at first, let's define it like this. I have prepared it, of course, before. I have it in my notes. So this is how I imagine it. For example, we want to create a class or an object with type rook. Here we are defining which color he will be. So of course the pieces above will be black colored, and pieces on the bottom, from like when you are watching or when you're looking on this from your point of view, on the bottom are white pieces, and up are black pieces. And we need to now, and in between of them will be the other elements in between of them will be non-types. This is pretty useful because with non-type you can do nothing. It will just represent here is nothing, only an empty square. Okay, let's just go ahead and let's define our pieces. So I have prepared my initializing method, and in my initializing method, as I mentioned already, I need to distinguish between the black color and between the white color. So I will define my self color will be equal to color, which I of course need to put here as argument, as a parameter. And then every single piece will have its own image ID. We will be working with this image ID in relation with the pillow library, which I have mentioned at the beginning. At first, it will have like non-ID. The image ID will be defined when we will define the certain type of piece. And also for future, it will be pretty useful if we know if the piece has moved or not. This attribute will be mostly used when you will be interacting with pawn, because it has like different rules when the pawn has already moved and different rules when he's about to make the first step. Okay, so what I have prepared are my images. I have those beautiful, cute kawaii images from website vexels.com. In this website there are like multiple pretty nice PNG images of various styles of pieces. So if you do not prefer something like this, definitely you can choose something else. But I have chose this vexels.com website. All those images were for free to me, and you will also definitely be able to find something what will be suitable for you. Or also there are like many other websites in the internet So just feel free to pause the video. You have to keep in mind that you need to choose, of course, the format PNG, and all the images has to have same width and height, so it has to be a square. Okay, so we are now going to import we are now going to import our pillow library, but we don't need like everything from the library because the library is pretty huge and can provide you like various things. But from our pillow library, we need to import an image and image taking. Okay, so what will be definitely same for every single piece is that every piece must have a piece image. We need to set parameters as self and image size. For size, we are of course using our well-known single one hard-coded square size value. Now we are going through some pillow library specifics, so I'm just not going to explain those like super deep. So we need to take our image and we are taking a method open, and we need the path of our every single image. Then we are now saying take that image and resize it. So image resize, and resize it needs to be a tuple. The recursive size in pixels to tuple, as you can see. So width and height, what will be my width and height? It will be the very same because we are still talking about squares. And now we need to put this into the self piece image is equal to image take that photo image, and as a parameter will be my image, and we are returning our self piece image. With this value, we are able to move the image through our canvas. This will be like very unique value for every single image. So we are preventing some mess using this method. Then let's say let's define every single class. So our very first class will be pawn, and the pawn is of course inheriting the class piece as every following one. And during initialization we need, yes, now I have already like inherited it, so Visual Studio did this instead of me. And now we need to define the self path. This self path we need to define. So our self path will be, I'm using formatting here. I just keep in mind to name your images like clearly, because now I have like pound B, pound W. So now I will just use the path image slash pound, and in curly brackets I'm putting the color, because as we have defined here, our color is either B or W. So using this, I don't have to like define if color is white, then use this image. If color is black, use this image. Now I just can make it in one line, and it's pretty good. It's pretty readable. And of course we need to define ending. This will be like very same for every other class, but with different name. Now we have our rook. We can rename this. Then we have a bishop with this name. Then we have knight with a very same name. Yeah. And king and queen. I hope I did not forget anyone. Queen. Okay. Okay, nice. So let's just display those into our board graphic. In order to do this, we need to come back into our board graphics, into our visual representation, and now we want to put pieces in it. I can make some comment here because it's already getting a little bit too big. So put pieces, and again we are looping very similar to before for row in a range 8. This is what we already know. For column in range 8. We are now defining our piece. We are now going to use our board state, and from our board state we are going to use this method, but not like, we don't need the method, we need to initialize board state with this method, and we need to store it somewhere. So we can say this is the main board, and the main board is actually nothing else than init board. And of course we need to import all the pieces, because now the board state does not know about this. So from piece, also import everything. Now it's beautiful. And now we can say that we have our self board, the main board is equal to self board state dot main board. This is my reference to board state, and from board state I'm taking this value, this variable. So we want to now use this. I can define piece with type piece is equal to self main board, and we need the row and column. So now I'm accessing every single element of my main board, every single element of this list. I know that, for example, in C# or anywhere else, this won't be possible because we have, of course, here many other types, like known. But for us, it will be now easier if we will keep in mind, okay, this piece is type of piece. Or actually, if piece is not none, then just I will define an image. It will be equal to piece. And now I have defined a type as piece, because now I can do this dot image, piece image method. And I will use self square size. This is the image size which I was talking about. As you can see here, image size. I need this parameter, but I don't want it like as big as the square size itself, but like square size multiplied by 0.1. I want to like make it a little bit smaller. I don't want like 100% of the square side, but like 90% of the square side. And I just want to put it into an integer, because this would be some float, and that's not what I can put into resize. Can you see? I can put on a couple of integers, so I would get error if I would not do this. And now I have piece image. My piece image is equal to self canvas, and now we are going to use another method of canvas, create image. And now we have to, as you can see, create image item with coordinates x1, epsilon1. So now again, we don't need 4 values, but instead we need just 2. And this x1 and epsilon1 will be representing the upper left corner of our image. And I want to like somehow put it into the into my board. So I'm again going to use self offset plus column, because again that's the variable which is changing, multiplied by self square size. This is still very same thing as when we were drawing squares. We want to resize it using self square size divided by 2. That's my x coordinate, and now my epsilon coordinate is again self offset plus, now we are moving towards row, multiplied by self square size, and again self square size divided by 2, because I want to put it exactly in the middle of my square. And the create image attribute has an attribute image, and this is equal to our image. This is equal to our instance of image, because otherwise without this create image would not know what he has to display to us. And now as we have defined at the beginning, the image ID was none, but now we are already like initialized the certain type of piece, and we want to rewrite this value with the value of the image ID, because we want to then work further with the image ID. So our, again, this self main board that image ID, because think about this as about a certain piece. is equal to piece image. Okay, I'm sorry for this, I made a little mistake or two. So firstly, we can't use piece image, of course, because it's a variable. We need to use a method piece img. So I need to rewrite this in order to make it work. And another thing I have to do is that I have here imported this file, and this is like common beginner mistake, because when we would keep this file, this import there, it's what bring us to the circle import error. So that was wrong. And now we can try to run it now, and it looks so beautiful. It's so cute, those kawaii pieces. So we have put those pieces into our board. That's great, and this is exactly what I was talking about, the analogy. We have in the upper left corner a black rook, and also in the place in the code in upper left corner of our list is also a black rook. So this is like pretty good strategy, because then you are able to pretty good imagine how you want to move those pieces through the board. So now what we want to do is to make them alive. Of course, we want to make our pieces alive, and in order to do this, we need to make some rules. How can they move, and otherwise what we're not. So firstly, what will be the very same for all the pieces will be a method called check range, and of course we need self. And yeah, using this method, we will be able to check if the player or if the user of the game don't want to click somewhere randomly outside the board, or somewhere on some square where the piece can't be placed. So we definitely can move our pieces only within our grid 8x8. So we will need also another two parameters, and it will be a row and column. And we can say if row will be greater than 7 because we are moving in the indices from 0 to 7, or row will be less than 0, because of course we can put it somewhere in the list with the index -3. If this statement is true, then return false. And also very same thing for column. So this will be like a policeman which is saying, okay, you can do this. And otherwise, if everything is alright, if we are within the range, then return true, and we are now saying, okay, you can move on. Another method which we want to define is, and where we will be using this check range method, is method called can move. Now we will be defining if the piece can move or not. So we will need a row, the column, and also the board list itself. Board list. Yeah, so this board list is of course this board list. Okay. Now if check range will say, okay, everything is alright, we can like we are within the range, no rules were broken, we have to put there, of course, our row and column. Yeah. Then we can say that if board list row and column is null, because of course none are those squares where is no other piece, it's like empty, definitely we can return true because everything is alright, we can move there. Or also another thing we can do, or another, let's say, circumstance under which we can move on, is if this of course represents some certain square, and if the color of another case we can have is that we have on our square some another piece, but we can of course move into some square where is a piece with the same color as I am. So when I'm playing for like white pieces, when I'm like white player, I can step somewhere where is another white piece, but of course I can step somewhere where is a black piece because I can take him. So if the color is not equal to color of myself, then, yeah, sorry, only one equal sign, then return true, I can also move there, and otherwise return false, because otherwise, of course, I'm not able to move there. And also, yeah, and also if our policeman, if our check range said, oh, no, you can't move there, we also returning false. Okay. Now we will be using this can move method or above method when we will want to check like a valid squares where we can move. We will create a list of valid squares for every single piece. We will click on some piece and we will be like immediately able to see where the piece can move. We can make something like we can light on the squares when the piece can move, and then when we make a move we can light off those squares. So every single type of a piece will have its own method for a valid moves, because of course every type of piece is unique and has a unique way how can he move through the board. So let's start with the root. We will define a function called valid moves. This method will be like every other type of piece will have this method. Now we need as a parameter, our parameters, our current position. Like let's say I will click on my rook, and what I will be providing to this function is where I am right now. So I will provide the row and column where my rook is right now, and also I need my board list. I definitely need my board list because this is my map. Without the map I don't know where I am, I don't know nothing. So now let's say I want to return a list of valid moves. I want to return a list full of tuples, full of, these tuples will be representing pair x and epsilon, on row and column where I can move. So the good strategy how to move with a rook, because rook is pretty straightforward, like moving with rook is nothing difficult. You are just able to move horizontally or vertically. So I will define some, let's say, vectors. We'll create a list called directions, and these directions will be storing the 4 tuples, and those tuples will be representing x and epsilon axis. For better imagination, we can just see how I mean it. So with the rook, you can move only this way or this way or this way or this way. There are 4 possibilities how you can move with the rook. And every time when you want to move this rook this way, the x-axis is staying the same, the column is staying the same, but the epsilon axis is decreasing. If you want to move this way, the x coordinate is increasing and epsilon coordinate is staying the same, and so on and so forth. So when you want to move this way, how I said, my x-axis is, or x coordinate staying the same, so it will be representing by the 0, and my epsilon coordinate is decreasing, and I will represent it using a -1. Other way around, when I want to move this way, my x-axis is staying the same and my epsilon coordinate is increasing. So I can say 0 and 1. 1 will be represent an increase, of course, and when I want to move horizontally, then my x coordinate can increase and epsilon is staying the same, or my x coordinate is decreasing and my epsilon coordinate is staying the same. Now we want to loop through those directions, and we want to evaluate if the place, or if the square where I could eventually move is okay. So for x and epsilon, of course, this is x, this is epsilon in directions. I will say that for, let's say, step in a range from 1 to 8, this will be, of course, representing like all the possible, like my whole range of the grid. We are now starting from 1, because if you would multiply something by 0, you would get 0 and it would have no effect. So we want to now evaluate if I can move this direction. So I want to evaluate a new row. The new row will be a row plus, like my current row where I am right now, plus my step multiplied by my x, by, in this case, 0. So in this case, my new row will be still the same as the previous one, but what is more interesting, my column, my new column, will be changing. So step multiplied by epsilon. Now we need to create an if statement, and we need to really use our policeman, which we have defined here, our policeman. We will use our self-can-move method. We will provide it with a new row and a new column, and of course our map board list. And now our policeman will evaluate if it is valid for us. And if it is, then we can append this tuple or this pair, this new row and new column into our result, which will be then returning. Otherwise, if our policeman said no, you can move there, let's say else, just break. But we are not end with this, because we have evaluated, let's say I have there no this pawn, let's say this pawn does not exist, and this hallway is empty for me, for this black rook, and our policeman is only saying if it's empty or if there is a pawn which is not my color, then you can move there. And it means that both this square and this square would be valid for me, and I could go with my black rook on, I can choose which one I want to take, which piece I want to take, and this is of course not the way how you should play chess. So we have to add another if statement where we'll be saying that if our board, like this will be of course representing the certain square, if it's not empty, or if it's not null, and it means it's not empty, it means there is some piece, and if the color of the piece is not equal to my color, then it means I can move there, but please break, because you can like jump through it, you just have to stay there. And the end we want to return result. Okay, almost the same logic we want to apply for a bishop with a single difference. Break with one single difference, that bishop can move horizontally or vertically, but it can move diagonally, so in this way or this way. So for this purpose you have to increase, like when you want to, for example, move this way, you need to decrease y-axis, but you have to increase an x-axis, so it can't stay like 0. So we want to, when we are moving this way, we want to increase x-axis and decrease y-axis. Then, like, I will make it a little bit faster. We want to decrease x-axis and decrease y-axis, and then I want to decrease x-axis and increase y-axis, and I want to increase x and increase y. So all combination of 1 and -1. Okay, I think this is like everything for bishop. And now let's say I want to apply this also for queen. Queen is the most powerful piece in the game, but it's just a combination of moves of bishop and rook. So we have here the moves for rook, we will add moves for bishop, and that's everything. Literally, there's nothing more you can do. Okay, let's say we want to move to the king. King can move. King can move also all the direction as queen. All the direction as queen, with the difference that it can move only by one step. Like can go through the whole board. So we will use the same logic here, and yeah, not very same, but we will take our current row and the X. We are now like moving only by one, so it's like more simple. Then we will take our column plus epsilon in our board list, and we will append this. If it's valid, we will append this into our result, and we will return the result. Okay, this is all for king. For knight, it's a little bit different piece, but it has also a pretty good pattern, because knight can move also almost all the directions, but knight can move like this. For example, we want to move our knight from here to this square. We are decreasing by 1 our x-axis and decreasing by 2 our epsilon. So this will be like only combination of 1 and 2 and -1 and -2. So I will just make quick decreasing x, increasing x, decreasing epsilon, and decreasing, increasing, also decreasing, -1, 2, 1, 2, 2, 1, and the very last remaining combination is -1 and -2 and 1. Okay, and all our things should be similar, like for king. Yes, this is very same as for king, and we have the only one who's remaining is a pawn, and the pawn is the most difficult piece because it has no pattern like this. You can't program it like this, because pawn can, at the very beginning of the game, when the pawn did not move, he can move by 2 steps. But when you already moved with him, then it can move by 1 step. But if diagonally, if pawn has a piece nearby of it, which is a different color, then he can move the direction. So it has like no pretty pattern like this. So it will be like a little more complicated, but like nothing super difficult. So this is the very same like for everyone else. And now we have to distinguish between the case if our color is white or or black. So we could be a white colored and we could be black colored. It's because when we are moving with our white colored pawn, we are decreasing an x-axis, an y-axis, and when we are moving with our black pawn, we are increasing y. So there have to be different. Now we can say if our map, if our board list, we will take a row, decreased by 1, and the column will stay the same. Yeah, this is like the basic move when you will moving like one step forward. Then result append. Oh, sorry. If this is none, append into our result tuple of those two. Okay. Then another case could be that our column is -1 when it's greater than 0, and for the list row -1 and column -1. It's not none. And we can like close it. Okay, this will be like a long condition. And the place here, when there is a piece, so it means it's not none, but there is a piece, and the color of the piece is not equal to my color. Then append row -1, column -1. Okay, so what we have to do here is we have moved our white pawn -1 row and -1 column. So if here in this place would be some piece with a black color, I can move there with this one. Then the very same thing, but if you want to move right, if there would be a pawn, that means we would also decrease our row and increase our column. So we will increase it. The very last thing for a white pawn would be that if our property has moved is equal to false, and I will take this, and our row -1 and column is staying the same because we can move only straight forward. Column is none, and also plus -2 -2 is none, then you can move 2 steps forward. You can move 2 steps forward. Okay, like how I said, with pawn it's a little bit more difficult and it looks maybe messy. I hope it's like not so overwhelming for you. But what we have done here is just that I have checked, okay, I did not move, so I will be able to move like 2 steps forward, but I have to check, is this empty? Okay, is this empty? Okay, I can move to like, I can move -2 and column is staying the same. Okay, and the almost same thing, but we will just change our plus and minus signs. Will be if our color will be black, I will copy paste this. I'll copy paste this, and now I will be increasing. This will stay the same. This I will be increasing, and also this and this, and yeah, now if our column +1 will be less than 8, because of course we can move like beyond the board when the pawn with the black color will reach opposite side. And yeah, row +1, column +1, and +1. Okay, and this will be also +1, +2, +2. Okay, I hope it's everything. So now we have finally defined how our pieces could move, and now what we are going to do is to move to the board state function, and here we need to be able to trigger clicking into the board, and then also we need to recognize in which squares are we right now, did we click right now, and incorporate it into our graphical board, and also use our piece class. But before we truly start, I have forget one thing. I need to return a result if I want it to work properly. Okay, and now I can move on to the board state, and here I can define a function using which I will be able to handle or manage our clicks into the canvas. I will use this function with another method called bind. It will provide me an object called event, and what I want from event, I want his x attribute and I want his epsilon attribute. And let's say I want to print those, if I want to show it to you. So I have those. I need to move to the chest because here is where my main object is defined. And now I need to take the canvas object from my chest. I need to use the method bind. I need to determine which event is going to trigger my desired function, and my desired function is chess board state. So from my object chess, I'm taking object board state, which we have defined here, and from my board state I'm taking an method handle click, which I have defined now, and just be aware, please do not call the function like this without brackets, please, because we do not need to call this function. We just need a reference on this function. This event or this button one represents the left click of the mouse. So when I do a left click on the mouse, this event, this function is going to be called. And now I think I can try it if it's to what I want. So it should print x and epsilon coordinates, and how we can see it really do what we want. It's really printing x and epsilon coordinates. Great, this is exactly what we wanted. But now, this is not everything, of course. We need to determine where we are clicking. So it means I need to define somehow that only those clicks within my board are valid. Those clicks are not valid for me. Only those within my board are valid. And not only that, I need to determine where the upper left corner is beginning, is the beginning of one position, and the bottom right corner is the end of determination of this one square, for example. And I want to apply this strategy for all other squares. So for this purpose, I need to create a function called create positions, and this needs only self. So what I'm going to do here is that we are going to determine from where until where I have this square. So this square would have values 0, 0. This square would have values 0, 1, and so on. I want to click everywhere in the square, and still a player will know, okay, I have clicked on this pawn. So for this I need values from my chess, for my board graphic. I need exactly those values. If I want to determine it, I can say those will be my sizes, and I will the name remain the same, but I just want to take this object, and from this object I want to take the value square size, and also from the object for graphic I want to access the value label size, and the very same thing for the value offset. Okay, now I have everything what I need for my create position method, and now I will define some list called positions. I will be returning it also, and in my positions I will use very similar strategy as before. So for row in range 8, and for column in range 8, I want to append into my positions one tuple which will be containing everything what we need. So what we need is the coordinate of upper left corner and bottom right corner, and the values of like the information about that square, like which one it is. So I will say my upper left corner will be row multiplied by self square size plus offset, because this this was the space which we defined between the border of the canvas and border of the board. Almost the very same thing will be for column. This is upper left corner, and now we need a bottom right corner. So it will be very same. The only difference will be that I have to increase this value by the size of my square, and also very same thing with only one difference will be for epsilon axis of bottom of corner. And now I want to also append that certain information, the thing which really interested me, and that's which column and row I am in. Okay, I have this. Somehow I want to create those this list already during initialization of board state. So I can say self positions equal to self create positions. And now I want to determine, I want to find out if the click which I made was valid, if it was within my board. If my column is greater than x1 and my column is less than x2 and my row is greater than epsilon1 and is less than epsilon2, then I know, okay, I'm in the range where I want to be. Yeah, sorry, I have to loop through. For x1, epsilon1, x2, epsilon2 positions in positions. Okay, those are my values. Self. Okay. Now it's great. So this is the value which was provided to me from my bind method, and those are the values which I have determined here. Those are values which are determining where, like, which squares I have clicked on. So if I'm within that range, let's say I want to print position 0 and position 1. So it means I will print my column and the row. If I call this right now, I have clicked here, nothing happened, and I have clicked here and I see, okay, this is row 1 and column 0, and this is row 0 and column 7, so it's exactly how I want it to work. Okay. Now I want to return a little bit to our board graphic part. I just want to firstly create a functions for lighting of the squares. So when you will click on some square or when you click on some piece, then it will light on the squares, the valid squares, when you can move your piece which you have clicked on. So for this purpose, we will very little modify this loop in init draw, we want to add to every single square, we want to add a tag. A tag will be something like identification number, like ID for every square. So because what I have to do is that I have now, when I have created my grid, my squares, I fill it with some colors, with black or white. But when I want to change the color of the square under some circumstances, then I have to choose which square I want to modify. Sorry, vice versa. Row, column. So now I can distinguish between every single square, because this tag will be unique for everyone. Now I want to create two methods. First method will be called lights on, and in this method I will need self and our well-known valid squares, which we have returned here. So it will be literally called valid squares, and of course this method we will be calling in the board state class. So now I want to loop through this valid square for row and for column, because if you remember properly, we have our valid square, our result is made of tuples, where are those pairs row and column. So in valid square list, I will be looping through this, and now I want to get a color, the current color of every square, which is inside my valid square range. So now for this I need to use a new method of our canvas object. It's called item get. I will get an item. Our item will be our rectangle with some certain tag, and I will now say which tag I want to use. You see here is a tag or ID. So this F is for formatting. Sorry, I forget to mention this. This F is for formatting of string. And so we are going to use the very same tag as here, so I won't make a mistake. So using this, I'm able to choose which certain square I want to modify. And then now I need to find out which color is that square. So for this purpose, I will use attribute fill, which we have used in filling and in determining which color we want to fill our square. And now I have here prepared some colors. Let's say this is my white color of my white square, and this is the color how it's going to look like when it will be like, yeah, this is a valid square. It's like those light black, light white, those are like colors in between green and blue. So the player will be really able to perfectly see, okay, this is a valid square for me. So if a color is equal to white, then please change it. Self canvas item config. So using this method, I have a get a certain square, and using this item config method, I'm going to change that attribute which I want. So I will again take this tags RID is equal to this, and I need to determine what I want to change. I want to change my fill attribute, and I want to change it with self white, and a very similar thing I want to do for black color. So if the color is white, then just please change it to self white, and else if the color is black, then please change it to light black. Okay, this is a function for lightening on the squares, but when we make a move and now the second player is on turn, we don't want to keep it in that color. We want to change the colors of the squares as they were before. So when I will be determining when I will be calling light on and light off methods in the board state. But when the light off method will be called, I will provide it with the same values. So the valid off method know which certain squares should modify as they were before. So this will be like almost same, just vice versa. So if it will be light white, change it to white, else if it will be light black, change it to black. Okay, those were functions which I wanted to make before we move further to our handling of our click. Now I want to define some variables which will be pretty useful. We can say those will be something like state variables, because before we move on, we have to determine some variables which will be which will say us in which state we are, if we are picking a piece or if we have already picked some piece and we want to put it in some desired and valid square. That could be something like is picking. If the player is picking, first of course when we are starting the game, it could be only true, because when you are at the very beginning of the game, firstly you have to pick some desired piece. Then another thing which we have to determine is turn. So we have to say who is on turn, if it's the white player or black player. At the very beginning, every time white player is about to start the game. And also what we need is a self click position, variable, which will be at the beginning none, but this click position variable will change it. We'll be storing here we'll be storing the position, the row and column of the picked piece. Okay, so instead of this easy print, of course, we don't just want to print where we have clicked, but we want to work with those data further. So we can say we can create a method called handle square, and the handle square will need 4 parameters. First will be the row, then column, and then x and epsilon. We will provide those values here in handle click. So let's say handle square, and want to feed it with those values. So those will be the values where I have clicked right now. And also I want x1 and epsilon1 values, because this will be like determinant. We will use this when we will want to move the image of our pieces, when we want to move to some certain square, and like the upper left corner will be, let's say, a delimiter for us. So we can delete this, and now we can define our handle square function. So at first, let's define what's going to happen if we are about to pick some piece. So if self-picking is true, I hope I set it to true. Yeah, okay. If self-picking is true, then I will say that my piece, which will be type piece, will be equal to self board and main board, be equal to main board, because this, our main board is this. Yeah. So we will access some certain piece using the row and column. And now we can further analyze this piece and maybe work with this piece further on. So at first we have to find out if it's not just empty square, if it's really a piece, if the player just don't click randomly somewhere on some empty square. So if piece is none, or if piece color is not equal to our term, because yeah, there are two cases. One case is that the player just randomly clicks somewhere on the empty square, or it could click, for example, I as a white player on turn, but I have randomly clicked on some black player, but I just don't want to do anything. I just want to return. Don't do anything. And this is probably not the most satisfying solution, because piece should be type of piece. We are not saying if it's none. That's not pretty good. So changing like this. Now, if one of those conditions are met, then just don't do anything. Don't change my state is speaking. Don't change the who is on turn. Don't change anything. Just return. But if those conditions were not met, let's just edit our click position. Okay, I have a typo. Let's just change our click position with those positions. It will be like a row and column. And now I just want to light on those squares. So if I have clicked right on my white piece, then I just want to, I can say here y on, I want to determine my valid squares, which I'm going to use. My valid squares will be my piece and our piece have, every our piece have method valid moves. So valid moves, and what we have to provide? We have to provide a row, a column, and main board. self mainboard. Now we have our wallet squares finally, and now we want to use our board graphic object, and we want to use a light on method, and we are providing our light on method with a valid with wallet squares. Okay, and when everything this happened, then I have picked my piece successfully. Then I want to set is picking state to false, because I'm not picking anymore. I want to put the piece, and if I'm in the state of putting, then I'm going to determine like new piece will be equal to this. So it will be like the new piece will be like the place where I have clicked. And what I want to do now is to literally move the piece. So I will say move the piece. But before, I have to validate if my main board, I'll be using now the self-click. I'll be now use self-click position. I'll be using those row and col, which I should already define, but I'm going to now say if it's none, then please just do nothing in order to somehow prevent some mess. So is not none, and if my row and column is in self valid squares, because this is like the row and column where I have clicked right now, I assume that it's not none. Those click positions are none, and I'm now going to check if they're in the valid squares, because I have of course moved my piece only when they are within those valid square list. So if all those conditions are met, then just take self main board, literally override, for example, literally override this none by this certain pawn. Okay, so for example, I want to move with this pawn 2 steps forward, so I'm literally overwriting this none with this pawn B. So, and this is representing my row and column where I have clicked right now. So rewrite it by this value, okay? So this is representing, for example, my none, and this is representing my pawn. Okay. Please, to prevent again some mess, rewrite this place by none, because I have already made a move, so this have to be empty right now. So please make yourself empty. It will be none. And now what I want to do, I want to literally move my image of my piece in that certain place. So I will use another canvas method called chords, which using which I will determine, I hope I will write it wrong, I am now providing my chords function with an piece image ID, sorry, this piece is this piece, okay? I think I will save it into self because it can maybe make some mess. Okay. And now I have determined which piece I want to move, so which certain image I want to move, and now I have to determine where I want to move. So for this I have those x and y, those upper left corners of the square where I have clicked. So I will use my x plus self square size divided by 2. As I have mentioned before, we have to do this because we are using x and y. We are determining where will be the very middle of the image. So the same thing for epsilon coordinate. And now what I want to do, of course, I have lighted on my squares, and now when I have successfully moved my piece to the position where I want to light off the squares which were previously lighted on. So I can say lights off. And here I will use our board graphic object. I will use the method lights off. I will provide it with valid squares. Yeah. And I will also set my picking state to true, and also we want to change the turn, so turn will be I think I will make a function for this because it will be like more handy. I will make a function for set turn, and we will be changing the turn. So if self turn was equal to W, let's change it to be like black, and else please change it to white. Okay, and now I will call this function, so set turn. And also what I want to do is to set my click position again to none, because I don't want to work with some data which are now obsolete for me, so we have to like delete it to make space for new data. I think we can try what's going to happen. So we can try, we have no error, that's right. Oh, beautiful. So this is exactly what we want. We see the rules, looks pretty nice made. You can see where everywhere I can go, all valid squares are lighted on for me. I have make a move and they will light on. That's beautiful. Our handle square method is not perfect yet. There are a few things we have to add. For example, right now we are not able to change our mind. As you can see, I can just click here, but if I want to change my mind and to move with another piece, it's not possible. And it's not like very user-friendly. So we need to change this. Let's say I have changed mind or change the piece within one turn. And now what I want to do is literally say that if my new piece is not none and the color of my new piece is equal to the self turn, then just please at first lights off, turn off the lights, because those which were valid for us are obsolete for our now because we changed our mind. And of course we need a valid square to put here. Then we again want to change the cell is picking to true, because we have picked something and we have changed it to false, but we want to pick again, despite of the fact that we did not successfully make a move. So despite of the fact we want to change is picking to true, so we will be able to move here. But to be able to move here, we need to call this handle square function again. So this is like beautiful case for recursion. So we have changed the state and we have now called the function again, but now it will have a different scenario because is picking is equal to true. And also we need the same parameters. Okay, this should work. One more thing which I want to do is that I really want to make this bulletproof. So I want to just say that if click position is none, then please don't do nothing, just return. And also one last thing which I want to do to make it like totally bulletproof, just to prevent, to say if row is equal to the, if we have clicked on the same piece twice, then please just do nothing. Because without this statement, it could do maybe real crazy thing. So if row which we have clicked, if the new row which we have clicked is the very same as the row which we have stored before, and also if this is for column, then please just do nothing, return. So now let's try it, and now as we can see, we can change our mind as many times as we want. So this is nice. Cool. Okay, now let's enhance a little bit our board graphic. This is still not everything, this is still not enough, because we need to, for example, what I want is when I will take some piece, for example like this, I don't know which piece I have taken anymore, like it's unknown for me. And I want to like store it somewhere so it will be visible for both players which pieces have been already taken. And this is also like a little bit confusing. You are not sure who is on turn. You just have to try to click. It will be nice to see who is on turn. So at first, let's add here some space to our canvas so we'll be able to see statistics. Okay, so now let's just very quickly create a function called draw stuff, like statistic, which will just do a graphical thing for us. So it will draw a board or space for statistics. I will go through this like super fast because this is pretty self-explanatory and there's a lot of easy math, but it took me a while until I have figured out which values are like best. So this is also maybe a thing you will be playing on your own a little bit until you will reach the design which you want. How I said, it's nothing difficult, but just a lot of playing with numbers. So at first we want to create like board, like a space for our statistic. Then we want to create a text, and in the upper part will be text white, like white player, and down or in bottom part will be text black, like for a black player. Of course, you can choose any design you want because there are endless possibilities how you can play with this. These are literally just values from my notes, which I have been playing with before. So this is x and y axis for my text, and now I will set that I want to fill the color of my text should be solid black, because this will be text for a black player, which will be in the upper part. And now I want to set a font. I will just copy paste this from my notes, because as a font, don't forget to put the information about your font into the tuple. We need to choose a tag because we will be playing with this text further in our setTurn function. And of course, the most important thing is what will be the text itself. And also we will do the same thing for a white player. And at the beginning, I wanted to do it in the way that the player who is on turn, that player will have this text bold, and when it's not on turn, it will have a normal text. So at the very beginning, when we draw our statistics, the white player is on turn. So I will set this to bold. And now I want to use this function in my initDraw method. So I will call here self-draw_statistics, and also I will just use some values which I have prepared before, because really this was a lot of playing with numbers, and it's nothing like funny or nothing interesting. It just I have to play a lot. Okay, you can see what we have created. Oh yeah. At first, we have to make our canvas bigger, because of course the sizes which we have now are not enough. So I will change the canvas width by self square size multiplied by 5, and now we should see the result. Yeah. Okay, almost. Almost. I have made some little mistake. Yes, I have used the same coordinates. That's of course wrong. So I will use this, and also I will use another color which I have defined before. So now it looks good. As we can see, the white is unturned, so the white one is bold, but it's not. Now it should be like a normal text, and this should be bold. And this we are going to achieve using those tags in our set turn methods in board state. So now if our self turn is equal to white, please just take I will again use the item config. Just take the certain object with a tag or ID equal to white, because that's how we define it. Then please fill this. If we would not fill this with the same color as we did it in our board graphic class, then without the fill we would have the default color for the text, and that's not what we want. So fill it with self. I will take those values from board graphic, and the object board graphic have the color white stats. And now I will take the same font and okay. So when white is unturned, make it bold, and please take a black one, set it to black, I hope, yeah, black, and don't make it bold, just make it normal. And else, if black one is unturned, then take a white one, make it normal, and take a black one and make it bold. Okay, let's see if it works. So we have white, we make a move, and now the black is like highlighted. Nice, that's exactly what we want. And now we want to, if someone is going to, if I take a piece, I want to make this black pawn appear here. So let's just go ahead and let's create a method for this. So firstly, we need to move to our board state, and here we need to define a new state variable. In this variable, we will be storing which pieces have been already taken, and I will literally call it like taken pieces, and it will be actually dictionary with only two keys. First will be W for white taken pieces, and it will be containing only an empty list, and we will be then appending to this empty list the pieces if some conditions will be met. And then also the same for black ones. And now let's just fill those empty lists. We will returning to our, I think, the most important handle square function. We will define here another case, and that will be the case if we will take a piece. So if we will take this new piece, if new piece is not none, so it's not an empty space, and also new piece color is not equal to the self term, then we can say that we want to access self-taken pieces. We want to the key. Let's say the key will be new piece.color, because of course new piece.color will be only equal to W or B as we defined above. So we have accessed the value through this key, and we want to modify that value. We want to modify that list and want to append into that list a new piece. So we have appended a new piece, and now we have only filled our variable for state with needed or necessary data, but now we want to also literally display it physically on our canvas which piece were taken. So for this purpose, I will create here in chess in our board graphics, because it's something that will be responsible for visual representation. I will create a function called showTaken. I'm not going to explain this method super deeply, also because this would be really boring part. This is also just a lot of math. If you want to place it pretty side by side every piece into one row in our statistics board. So I will just do this very quickly. What I have found out is that in the sizes which I have now, it's nice to have 8 pieces in one row. So when I will take an 8th piece, then I know I have to display all other taken pieces in the row above, in the case of white, and in the row under in the case of black ones. So I will here define some row counter for black pieces. I will start from -1 because this was the value which fits to me the most. Now I will be using the function enumerate. So I'll be using an index and also a certain element of our list from our dictionary. So self board state, I will take from the object board state taken pieces, and from this I will take the black one, and of course I need here in. Okay, so I'll be looping through the list of black pieces taken. If my index is divisible by 7 because we are starting from 0 and I can fit there only like 8 pieces. If it's divisible by 7, then please increase my row counter by 1. And this is the boring part which I was talking about. I just want to change the coordinate of the piece which I have taken right now. And this is, I'm just very poorly going to copy paste from my notes because this was like really a lot of boring math. This is board size. Okay. Really, the only like interesting thing about this is that I'm using this index in order to like increase the value of x coordinates, so I'm able to move my piece nearby another piece, nearby another piece, and so on. There could be also another case, so I want to also loop through the white pieces taken. So this will be like W. And I hope this is right. Oh no, it's with, yeah, no, this is right. Okay. And I will also define some white row counter. We'll also start from -1. If yeah, I can copy paste this. If this condition is met, please just increase my row counter by 1. Okay, and also move the coordinates of the taken pieces, of the image of the taken pieces somewhere. So piece dot image ID. I will take this and I will also just copy and paste this because it would be like super boring if I would be explaining this. Okay. This should work. Sorry, this should work for us properly. So I have this method and I need to call it here. Of course, I have taken a piece, so now I have to call this method. So I'm use object board graphic and I'm taking a method show taken, and it needs no parameter. Okay, let's see what's happened if I will. Oh, nice. This is exactly what we want. This is great. Cool. This is really cool. Yeah, another thing which is definitely annoying is that I have a bug here. So my pawn have already moved and still can make like 2 steps. That's not right, of course. We need to change it. Here I will take that object, and when I have moved it, then I can set it to false. Okay, maybe now it should work properly. Okay. Sorry. True. Yeah, now it will be definitely working. But what is like the most important moment and most interesting moment in the game is that when I will take a piece which is type king. So I need to think also about this important phase. So I will take my piece. In this instance, we'll find out if my piece is type of king, and if it is, do something. I will also put it here for white mates, and that something will be some method. We can call it like endgame. So I will say end game, and I can call it here. So I will take board state object, and I will take endgame method. The same thing I will do here. And now we are almost done with our game, so we have to define the end game method. What we want to do when when someone wins. So what I want to, or how I imagine it, I have created this button, which also like PNG format. There are like so many websites. You can type something like web button creation or web button design, and you can make your very unique and beautiful button. So we want to use it now. I will define self button is equal to, I will use this. I think I have to import pillow library also here in my board state. So I need an image, take a photo image, and the name of the file will be this. So okay, I have here defined my button. Now I want to set where the button should be placed. So I will create a variable called playgame, and I will take, I also need to import here, take an inter, because we are going to use it. Sorry. Because we need to place the button. Or maybe we could do this in our board graphics, but okay, I'm just doing it already here. So I will say take an inter button, and we need our self board graphics root, and we need an image. This is our self button. Self button, I will set a border to 0 so it will look like nice. And I will have to set a command. So I need to put here a reference on some function which will be called or executed when some event will be triggered, and that event will be when we click on the button. Sorry, I think I'm going to define it here because it makes like more sense to me. Okay. So I need to define some command. we will define a comment which will be setting a new game. That's what we want. When we want to play a game, we want to set a new game. So set new game. It will be taking parameter self, and this will do something. And if I want to use this, I need set new game. Again, I'm not calling it brackets, I'm just sending a reference to it. And now again, we want to place it somewhere. So it's a method called place, and we need to define our x-axis, that's self board size plus self board size divided by 4. Again, this was just a lot of trying of figuring out the right place. And also self board size divided by 2 plus self offset. Okay, we place the button. And now we want to set the new game. So what we need to do is to take this method. We will delete everything. We will delete everything what we have until now on our canvas. Then we need to set those values again, because we are setting new game, so we're setting it to the default values. What we also, that's not everything. We have to use board state, and also here, and also here. Okay, so we set those values on default, and what we want to do next is that we want to initialize a completely new list, like brand new list of brand new map, which is not modified in any way. So we can say that we can use exactly the same value. Self main board. Yes, self main board will be equal to completely new self init self board state init board. And also what you want to do is to redraw the init draw, to redraw everything at the beginning. And also very important thing which we need to do is to also make a brand new board here in board state. So we can say self board state main board will be equal to self main board. The very last thing we want to do is to destroy this button, because when we will start a new game, we don't want to still see the play again button. We just want to destroy it completely, and this method does not need any attribute or parameter. So, and during copy pasting and changing my mind, I made a mistake. So this is not anymore in the board state, but in myself in a board graphic. And also here I need to change the path. So let's try what have we made. Let's try if it's working. So I will do a really fast attack. Nice. We have a play again button. We have take the king, and the play again button was displayed. Now we click and play again, and we can play from the beginning. So this is pretty nice. This is pretty nice. So yeah, it was pretty everything for this video. I think was pretty a lot, but I hope it was like not too overwhelming for you, and also that my explanation wasn't too maybe annoying, because this was like my first video and I had been making a lot of mistakes and so on. So I hope you enjoy this. I hope you have maybe learned something new, and if not, that you have at least gained some motivation and some inspiration to do something creative. So there are of course a lot of things which could be like, added to this. For example, when the pawn reaches the opposite side, you can receive a pawn promotion, so you can choose some other type of the piece and you can exchange it with the pawn. Or also the castle, like the special move when you can exchange the rook with the king under some circumstances. There could be also a score for the players and so on. Like there are endless possibilities how to pump this up, and definitely it's totally up to you. I will provide this code on my GitHub. You can take some inspiration, you can copy paste it, you can enhance it, you can do anything you want with this. And I really hope you enjoy this, and I hope we will maybe see you next time. Definitely keep feedback in the comments. It would be so nice from you. So I hope you really enjoy this, and I wish you a nice day.